What is quantum entanglement? Imagine you have a pair of magical coins that are forever connected, no matter how far apart they are. When you flip one coin and it lands heads, the other coins, even if it's on the other side of the universe, instantly knows to land tails. This is essentially what quantum entanglement is like, except instead of coins, we are dealing with tiny particles like photons or electrons. Quantum entanglement is one of the strangest phenomena in physics. When two particles become entangled, they form a single quantum system where measuring one particle instantly affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance because it seemed to violate our everyday understanding of how the world works. The coin analogy explained. Let's expand on our magical coin analogy. In the classical world, if you have two normal coins and flip them, each coin has a 50% chance of landing heads or tails, completely independent of the other coin. The outcome of one coin tells you nothing about the other. But with our magical entangled coins, something extraordinary happens. Before you flip either coin, neither has a definite state. They exist in a mysterious condition where they are both heads and tails simultaneously. However, the moment you observe one coin and see its heads, you instantly know the other must be tails, even if it's millions of miles away. This isn't because the coins were predetermined to be heads and tails from the beginning. The mathematical proof we have presented shows that such hidden instruction explanations are impossible. Instead, the act of measuring one coin somehow instantaneously determines the state of both coins. Why Einstein was troubled. Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, was deeply uncomfortable with quantum entanglement. In 1935, they published a famous paper arguing that quantum mechanics must be incomplete because it seemed to allow for instantaneous connections across vast distances. Einstein believed in two fundamental principles. First, locality. Nothing can influence something else faster than the speed of light. If you are on Earth and your friend is on Mars, your actions cannot instantly affect your friends because information and influence take time to travel through space. Second, realism. Objects have definite properties whether or not we observe them. A coin is either heads or tails, even if we haven't looked at it yet. Einstein argued that if quantum mechanics predicted instantaneous correlations between different particles, then there must be hidden variables, secret instructions that the particles carry with them that predetermine their behavior. He thought quantum mechanics was like a weather forecast that could only give probabilities because it didn't have access to all the relevant information. The hidden variable idea. To understand Einstein's thinking, imagine our magical coins again, but this time suppose they are not really magical. Instead, imagine that when the coins are created, they receive secret instructions written in invisible ink. Coin A. If flipped on Monday, lands heads. If flipped on Tuesday, lands tails. Coin B. If flipped on Monday, lands tails. If flipped on Tuesday, lands head. With these secret hidden instructions, the coins would appear to be magically connected, but they would actually be following predetermined rules. Einstein believed something like this must be happening with quantum particles. Bell's revolutionary discovery. In 1964, physicist John Bell made a breakthrough that would forever change our understanding of reality. Bell figured out how to test whether Einstein's hidden variable explanation could be correct. He developed a mathematical test now called Bell's theorem that could distinguish between quantum mechanics and any theory based on hidden variables. Bell's insight. Bell realized that if particles really do carry hidden instructions, like our invisible ink example, then there are mathematical limits to how strongly correlated their behaviors can be. He derived an inequality that any hidden variable theory must satisfy. Think of it this way: if you and your friends are playing a game where you each choose one of two options, let's call them A or B, and you are trying to coordinate your choices based on secret instructions you received beforehand. There are limits to how often you can match or mismatch your choices in specific patterns. Bell calculated that with hidden instructions, the best you could do in certain correlation tests would give you a score of 2 or less, but quantum mechanics predicted that entanglement particles could achieve a score of about 2.83, clearly violating Bell's limit. The CHSH test explained. The most practical version of Bell's test is called the CHSH inequality, named after physicists Crosser, Horn, Simoni, and Hort. Here's how it works in simple terms. Imagine Alice and Bob are in separate rooms, each with a device that can measure their particle in one of two ways. Let's call them setting 1 and 2. They randomly choose which setting to use for each measurement. After many trials, they compare their results and calculate correlations. If the particles were following hidden instructions, the mathematical analysis shows that a specific combination of these correlations cannot exceed the value 2. But quantum mechanics predicts this combination can reach 2.83. When experiments are performed, the quantum prediction is confirmed. The classical limit is violated by about 41%. What the mathematical proof shows. The mathematical proof we have presented demonstrates several profound truths about reality. Hidden variables don't work. The mathematical derivation of Bell's inequality shows that no theory based on local hidden variables can reproduce the predictions of quantum mechanics. This isn't a matter of opinion or interpretation. It's a mathematical fact as certain as 2 plus 2 equals 4. The proof works by considering all possible ways that hidden variables could influence measurement outcomes and showing that they lead to constraints, the Bell inequalities, that quantum mechanics violates. Since experiments confirm the quantum violations, we know that local hidden variables cannot exist. Reality is non-local. The violation of Bell's inequalities prove that reality is fundamentally non-local. When two particles are entangled, they remain connected in a way that transcends our everyday understanding of space and distance. Measuring one particle instantly affects the other, no matter how far apart they are. This doesn't mean information travels faster than light. That would violate Einstein's theory of relativity. Instead, it means that entangled particles share a kind of quantum connection that exists outside our normal concepts of space and time. Measurement creates reality. The mathematical proof also suggests that quantum properties don't exist in a definite state until they are measured. Before measurement, entangled particles exist in a superposition, a ghostly combination of all possible states. The act of measurement forces them to choose definite states, and this choice is coordinated between entangled particles. Our everyday analogies. To help understand these abstract concepts, let's explore some analogies. The glove analogy, why it fails. A common but incorrect analogy compares entanglement particles to a pair of gloves. If you put a left glove in one box and the right glove in another, then ship the boxes to opposite sides of the world, opening one box and finding a left glove tells you the other box contains a right glove. This analogy fails because it assumes the gloves had definite properties, right, left or right, from the beginning. Bell's theorem proved this cannot be the case for quantum particles. Instead, the particles are in a superposition of all possible states until measured. The dance partner analogy. A better analogy might be two dancers who are perfectly synchronized but separated by a great distance. When one dancer moves left, the other instantly moves right, maintaining perfect coordination. But unlike predetermined choreography, their movements are spontaneous and unpredictable, yet always perfectly correlated. The mathematical proof shows that this coordination cannot be explained by any set of prior instructions or hidden signals. The dancers are connected by something more fundamental than classical communication. The quantum coin flip. Imagine a special quantum coin that, when flipped, doesn't just land heads or tails, it lands in a superposition of both states simultaneously. Only when you look at the coin does it decide which state to show you. Now imagine two such quantum coins that are entangled. When you observe one coin and it decides to show heads, the other coin instantly decides to show tails, even if it's on the other side of the galaxy. The mathematical proof demonstrates that this coordination cannot be explained by any classical mechanism. Common misconceptions. Misconception 1. Entanglement allows faster than light communication. This is false. While entanglement particles are instantly correlated, you cannot use this correlation to send messages. The measurement results appear random to each observer. The correlations only become apparent when the observers compare their results later through classical communication. Misconception 2. The particles were predetermined to behave this way. Bell's theorem mathematically proves this is impossible. The correlations observed in quantum entanglement cannot be explained by any predetermined properties or hidden instructions. Misconception 3. This is just a theoretical curiosity. Quantum entanglement has practical applications in quantum computing, quantum cryptography, and quantum sensing. The mathematical proof of entanglement has enabled technologies that are already being commercialized. Misconception 4. We don't really understand what's happening. While quantum mechanics is counterintuitive, the mathematical framework provides precise predictions that match experimental results to extraordinary precision. We understand the mathematics perfectly. It's our classical intuitions that need updating.